Great. So today we'll talk about the matched filter as demodulator, basically mainly in binary communication under Awgn. The idea is if we were to somehow process the incoming received signal by a filter, and our ultimate goal is to make a decision rule from the output of this sampled filter response, what should the filter be? The idea of the matched filter is to use a filter whose impulse response is a delayed and inverted version of the pulse shape itself. So in this case, we are focusing on a single pulse shape. Now the convolution with h of t, the filter impulse response, in the case where the filter is a matched filter, does pattern matching with the pulse shape and gives out the same output as the correlator's output at the sampling time, where the sampling time is the bit at the end of the bit interval, TB. So let's see the binary antipodal case. In the binary antipodal case, the received signal, as you know, is either it's S sub m times phi of t, the pulse shape, plus noise, where S sub m takes two possible values. Okay. Now we're talking about a bit duration TB. Okay, so for this case, the matched filter is defined as the filter whose impulse response is phi of TB minus t, where t lies in the interval 0 to TB. Okay, so as an example, consider this pulse shape and the corresponding matched filter impulse response is going to look like this. Okay, so this is called a matched filter. Why do we study this? Because we will now show that it's the output SNR at the output of the matched filter is maximized. So it is the filter shape that maximizes the output SNR. In general, it can be shown by an alternative proof that when we're going to consider the detector combined with the processing and the sampling, this matched filter output provides for us a sufficient statistic for making the minimum probability of error decision. But we will, I will post some reading material if you would like to read this generalized proof. In this class, I will just give you the SNR optimality, SNR maximization proof. Okay, so before we go on to the proof of why the matched filter maximizes the output SNR, let's first consider the orthogonal case as well. In the orthogonal case, as you know, we have two basis functions. So as a result, we cannot, a single matched filter is not going to do the job. We're going to need two matched filters. Okay, so we can use two LTI filters, each of which is matched to the particular basis function, whatever it is. Okay, and in general, if you had many signals, depending on the dimensionality of the space, you would need that many, as many matched filters as the dimension of the signal space. Right. So let's, again, consider the orthogonal case, meaning two dimensions. We'll have two matched filters, therefore two matched filter outputs, Y1 and Y2. Okay, and Y1 is the output of the output of the incoming signal, oops, going through the first matched filter sampled at time TB, okay? Notice that this is identical. This is going to be identical to the correlator output for that particular signal, gamma phi 1. Okay, so this is the correlator output that we are already familiar with. Okay, so and Y2 is going to be the correlator output of the receive signal with gamma 2. Okay, so we will make decisions then based on Y1 and Y2. We have a vector Y1, Y2 from which we're going to make the decision whether a 1 or a -1 was sent. Okay, now let's see why under Awgn matched filter maximizes the output SNR. So consider the receipt signal in general, which consists of the transmitted signal plus noise, where noise is zero mean Gaussian with power spectral density constant at n0/2 watt per hertz. Okay. Now this received signal is going to be passed through some filter, any filter. So let's consider this filter output. Y of t equals 0 to t. The convolution with the filter impulse response, in general filter H. Okay, but we can write this convolution in terms of the two components, the signal component and the noise component, S of tau H t minus tau d tau plus n of tau H t minus tau d tau, right? And then consider sampling at the instant TB. What do we find? We find Y of t equals, I'm not going to write the integral again. Let's call this ys of t plus yn of t, where yn of t corresponds to the result of this integration. Now, let me open up some a page to write notes. So now let's consider the SNR at this filter output, which is the power in the signal component divided by the power in the noise component. At the moment, I'm sort of assuming that the signal is deterministic, so I'm not using an expectation for the power. Okay, so let's evaluate this expectation of yn squared of t. This is integral from 0 to t. I mean, let's let t be tb for convenience. Expectation of n of tau, n of t, h of t minus tau, h of t minus t, dt, d tau. Okay, so now what do we know about this expectation? We know that this is, it's white noise. So this is equal to t, the delta function. Okay. And because of that, using the shifting property of the delta function, okay, sorry, there is an n0/2 here, sure. So n0/2, a single integral from 0 to t, right? And now t is equal to tau, so this turns into h squared t minus t dt. Okay, so this is the denominator of the SNR. Let's write the SNR again. SNR is ys squared of t. What is ys squared of t? It's really integral from 0 to t. H of, well, what is ys? Remember that from the previous slide. S of tau, h of t minus tau, d tau. So we have the square of this in the numerator, and in the denominator we have n naught over 2 integral from 0 to t h squared t minus t dt. Okay, so we are looking for the filter h to maximize SNRO. Okay, so for a given h squared integrated from 0 to t, what would be the shape of the filter h that would maximize the numerator? Essentially, it is equivalent to this question. Okay, so notice that by the Cauchy-Schwarz inequality, and let me give you Cauchy-Schwarz inequality here. For finite energy signals, the integral g1 of t times g2 of t dt squared is upper bounded by the product of the terms g1 of t squared integrated times g2 of t squared integrated, where equality here is achieved only if one of the signals is a constant multiple of the other. We can use this to upper bound our SNR out as well. This is less than or equal to integral 0 to t h squared of tau. By the way, before I do that, let me write this down. The numerator I can also write as 0 to t h of tau squared s of t minus tau. I'm sorry, d tau. I mean, by a change of variables, right? Okay, so the numerator I'm going to upper bound using the Cauchy-Schwarz inequality, 0 to t h squared of tau d tau, 0 to, I'm sorry, the capital T here. Capital T, 0 to capital T, s of t minus tau squared d tau divided by the numerator. 0 to t h squared of t minus tau d tau. Okay, notice that by a simple change of variables, you can show that these two are the same thing. And so this is an upper bound, and equality is achieved if s of t minus tau is equal to a constant times h of tau. So this tells us, in other words, that the filter that maximizes output SNR is given by the scaled and shifted version of our pulse shape, which says it's the matched filter. And the constant here does not really matter. it will drop out of the SNR. And the SNRO resulting from this is 2 over n naught integral 0 to t s squared of t dt, which is 2 es over n naught, where es is basically this symbol energy. So no matter what pulse shape we use, the SNR at the output of the matched filter is given by the symbol energy divided by n naught over 2, which is very nice, actually, very convenient. Let's return to our lecture slides. So maximum SNR we found depends not only on the not on the pulse shape, but on the pulse energy, in other words. So SNR out with the matched filter is ES over n naught over 2. So no matter what the pulse shape is, as long as ES is constant, the SNR output is constant. Yet the spectrum, of course, is going to be determined by the pulse shape. You will think more about this in not one shot, but continuous transmission, which is going to be in the next course, as you know. Now, let's spend just a little bit of time thinking about perhaps the frequency domain representation of the matched filter. Frequency domain interpretation, if you will, of the matched filter. So now h of t equals s of t minus t, right? So consequently, h of f is going to be as conjugate of f e to the minus j 2 pi ft. You can easily show this by writing the definition of the Fourier transform. So basically, in other words, the magnitude spectrum is equal to that of the pulse shape. Okay, the magnitude response of the matched filter is identical to the transmitted signal spectrum. Okay. On the other hand, the phase is shifted by a linear function of t. Okay, so the noise at the output of the matched filter has a power spectral density. As you know, when stochastic processes go through LTI systems, their power spectral densities are scaled, right? H of f squared and not over 2. So the power spectral density of the noise is shaped by the matched filter characteristic, which actually is identical to the pulse frequency domain characteristic. So the total noise power, which can be found by integrating this noise PSD over all frequencies, is basically very simple and not over 2 integral minus infinity s of f magnitude squared df. But what is s of f integrated? It's es. So es over m not over 2. Yeah. And oh, wait, I'm sorry. Es times m not over 2. Yes, times m not over 2. Okay, that's the noise power. Okay, so yes, the output SNR is PS over PN, which is ES squared over ES and not over 2, which is ES, okay, over and not over 2, which agrees with what we found before. So now that we have sort of shown the property of the matched filter as a filter that maximizes output SNR, let's then move on to the performance of the optimal detector for binary signals. Now, for this, we will assume that signals received in successive signal intervals are independent. I mean, this is an assumption that is sometimes referred to as a memoryless channel. When would a channel have memory? Well, when successive symbols undergo a phenomenon that is lasts across time and then changes gradually, for example, such as a shadowing by obstacles, etc. We're going to assume that such an effect is not valid, and each successive signal is independent. So the detector can then make a decision for each bit individually without having to look at previous bits or future bits. Okay. So one-shot decisions, symbol by symbol. Okay. The performance is going to be measured by the probability of making an incorrect decision, which is called a bit error probability. Okay. How can we express this bit error probability? The probability of bit error is the probability that the second type of signal was sent, and the decision we make is that the first type of symbol was sent. S2 was sent, and we decide that S1 was sent. Or S1 was actually sent, and the decision is S2. These are the two possible error events. They are disjoint events, so we can add their probabilities to find the total probability of either of these events happening. Right, so this is the probability of error. Any questions here? Okay, so as I said, the two possible error events are disjoints, and we can add their probabilities to find the probability that either of these error events occur. And these are the only two possible error events. Now let's express these error events, the probabilities of these error events. Now, S2 was sent and the decision is S1. We can use conditional probabilities here, okay? Remember, probability A intersection B is equal to the probability of A given B times the probability of B. This is the definition of conditional probability. Okay, so probability that S2 was sent and the decision is S1 is probability that S2 is sent times the probability that S1 is decided given that S2 was sent. Now, S1 is decided. What is this event? We're going to have a decision rule. Decision rule, which says to us that you should decide on S1 if the received signal out of the matched filter the sampled matched filter output, that is in a certain region R1. Okay? And decide on S2 otherwise. This totally makes sense, right? I mean, we have one matched filter output to decide upon, to decide based on. Okay, we're going to decide whether S1 or S2 was sent based on looking at the matched filter output. We haven't proved this, but this is the sufficient statistic for making a minimum probability of error decision. Okay, so if you're looking at the matched filter output, you would have, according to the value of this output, you would have a certain subset of values over which you would decide on S1, and all the rest you should decide on S2. Okay, there is no reason why you would have some set of values where you know, you haven't mapped either to S1 or S2. Okay, so we will, you know, basically we are focusing on a decision rule such that if Y takes values in a certain region R1, we decide on S1, and otherwise, that is, if Y is not in R1, we decide S2 was sent. Okay, we don't know at the moment what those regions are. So the probability of choosing S1, given that S2 was sent, is the probability that the matched filter output Y is in region 1, given that S2 was sent. Similarly, the probability of making an error given S1 was sent is equal to the probability that Y is in R1 complement, given that S1 was sent. Okay. Now we can then write these first terms, the probabilities, these probabilities here, if we know the conditional PDF of Y under the condition S1 or S2. Okay. Remember, last time we were considering these conditional probabilities under Awgn, so we will be able to use those. Okay, so given that S2 is sent, Fy given S2 is the conditional PDF of Y, and when we integrate this over the region R1, we find the probability that Y takes values in R1, given the hypothesis S2 is true. Okay, and similarly, this integral gives us the probability that Y is in R1 complement, given that S1 was sent. These terms are inherited from the above. Okay, and then well, what we can do is we can put these terms outside the integral because they're constant. We can put this outside the integral, and what we can do actually is to notice that PS2 is nothing but 1 minus PS1. Okay, so that allows us to express everything in terms of PS2, S1, and lose PS2. We end up finding this expression. So this is the error probability. Notice that PS1 here is just a constant. Okay, it's not a function of our decision rule. What we can optimize to minimize the error probability, is this part right here. We need to minimize this. Okay. How do we minimize this? Well, the minimum probability of error decision rule is to choose the region R1. Choose the region R1 as the region of values of y for which the inside of this integral is always positive, because that will then maximize the value of the integral and it will minimize PE. Okay. In other words, the region R1 is chosen such that Fy given S1 times P of S1 is bigger than Fy given S2 times P of S2 over R1. In other words, Fy given S1 divided by Fy given S2 is bigger than P of S2 divided by P of S1. Okay. This is the minimum probability of error decision rule in general. When S1 and S2 are equiprobable, they have the same probability, which is 1/2 each, then the decision rule is going to, minimum probability of error decision rule will turn to choose S1 if Fy given S1 is bigger than Fy given S2. Okay, and this is called the maximum likelihood decision rule. When two hypotheses are equally likely, that is the prior probabilities, PS1 and PS2 are equal, then the minimum probability of the error decision rule reduces to the maximum likelihood decision rule, meaning choose one if Fy given S1 is bigger than Fy given S2. Choose one if this particular value of y that you received is more likely to happen under the hypothesis S1. Okay. Under the same condition, using the definition of conditional probability, you can show that the maximum likelihood decision rule is also, is also equivalent to the map decision rule. In other words, maximum a posteriori decision rule, which compares the posterior probabilities of the two hypotheses, P under Y. Given I observed Y, what are the posterior probabilities of the two hypotheses S1 and S2? This is called the map decision rule. The map decision rule is equivalent to the maximum likelihood decision rule and equal in turn to the minimum probability of error decision rule when the two hypotheses are equally likely in binary hypothesis testing. So in next time, we will take it from here and we will compute actual error probabilities under Awgn assumptions. Are there any questions?